Nearly 20 years ago, an unprecedented opportunity arose to test a cornerstone of the electric universe hypothesis. Prior to NASA's Deep Impact mission to the comet Tempel 1, David Talbot and Wal Thornhill, co-founders of the Thunderbolts project, publicly registered their predictions for the mission based on the electric comet theory. As far back as 2001, Thornhill made a dramatic and highly unconventional prediction with respect to the potential energetic effects of the 800-pound copper projectile, which mission scientists planned to fire at the comet. He wrote on his website, holoscience.com, "The projectile will approach too quickly for a slow electrical discharge to occur, so the energetic effects of the encounter should exceed that of a simple physical impact, in the same way that was seen with comet Shoemaker-Levy 9 at Jupiter. If the arc vaporizes the copper projectile before impact, the comet will not form the crater expected. On the other hand, any copper metal reaching the surface of the comet will act as a focus for an arc." On July 3, 2005, 24 hours before the deep impact encounter with Tempel 1, Thornhill and Talbot published their complete mission predictions on the thunderbolts.info website. Because of the comet's low eccentricity orbit, they wrote that electrical interactions with the approaching probe, quote, "may be slight, but they should be measurable if NASA will look for them. The most obvious would be a flash, that is, lightning-like discharge, shortly before impact." And they wrote that temperatures from the event would be, quote, "much higher than expected from impact heating." They also predicted more energy will be released than expected because of the electrical contributions of the comet. And they predicted that the impact crater left by the NASA probe would be smaller than expected because the comet is rock, more similar to an asteroid than a loose conglomeration of ice and dust. Those predictions, as well as several others on the comet's composition and surface terrain, received stunning confirmation. Moments before the copper projectile struck the comet nucleus, NASA scientists were amazed by the bright electrical flash, shortly followed by an explosion much larger than they anticipated when the impactor contacted the surface. As NASA investigator Peter Schultz said at the time, "What you see is something really surprising. First, there is a small flash, then there's a delay, then there's a big flash, and the whole thing breaks loose." Nor did the projectile leave the dramatic impact crater scientists had expected. Just one piece of evidence that the comet nucleus was much harder than NASA scientists had expected. As reported by Universe Today, Swift scientists have seen a quick and dramatic rise in ultraviolet light, evidence that the Deep Impact probe struck a hard surface, as opposed to a softer, snowy surface. And in 2011, when NASA's Stardust Next spacecraft imaged the impact site, it revealed a far less dramatic crater than comet scientists anticipated. Following these events in 2005, the science tech website Wired.com published an article entitled "They Sing the Comet Electric," which outlined the successful electric comet predictions of Thornhill and Talbot. However, even though subsequent comet missions, including the ESA's historic Rosetta mission to Comet 67P, have continued to affirm the electric comet theory, while offering no evidential support for the standard dirty snowball theory of comets, we've yet to see a meaningful revision of comet theory at the level of institutionalized science. Much more on these points will follow as this presentation continues. For our purposes, it is appropriate to address both comets and asteroids together, because in the electric universe, the origins and behaviors of both types of bodies are vastly closer than mainstream astronomers have ever imagined. And as we shall discuss further, scientific discovery has only increasingly blurred the line between comets and asteroids, as demonstrated by the instances of, quote, surprising comet-like behaviors from asteroids, as well as the desiccated, asteroid-like appearance of the comet nuclei imaged to date. Consider the recent major surprise that scientists with NASA's DART asteroid mission have encountered. The acronym DART stands for Double Asteroid Redirection Test, and the target was the moonlit asteroid Dimorphos, which is part of a binary system with the larger companion asteroid Didymos. In September of last year, The more than 1,300-pound spacecraft crashed into Dimorphos at approximately 14,000 miles per hour. The after effects that scientists observed were completely unexpected and remain unexplained. DART's impact resulted in nearly 1,000 tons of rocky material being ejected into space, with the debris forming a comet-like tail. As also noted on the official NASA Hubble site, quote, "The mystery is compounded when Hubble records the tail splitting in two for a few days." Dimorphos's orbit was altered to a degree that NASA investigators admit cannot be explained by any accepted hypothesis. The Science Alert article states, DART's impact altered Dimorphos's orbital period, decreasing it by about 33 minutes. However, a group of researchers measured the orbital period about a month later and discovered that it had increased to 34 minutes, 1 minute longer than the first measurements. Even though it was a single impact from DART, some force continued to slow the asteroid's orbit, and astronomers don't yet know what that mechanism might be. The researchers state in the preprint of their forthcoming paper, "We find that no mechanism previously presented for this system can account for this large of a period change, and drag from impact ejecta is an unlikely explanation." A Phys.org report states, quote, "The period of Dimorphos was observed to be slowly changing, but," the researchers wrote, "even that amount of change can't account for the difference, as it was 4 orders of magnitude too small to account for the difference we see. Therefore, whatever effect was causing the orbital decay before the collision cannot account for the discrepancy we observe. This includes the binary Yorp effect, mutual tides, differential Yarkovsky force, nodal precession, and mass loss," they said. We should note here also that a few years ago, the asteroid Bennu, which was a target of NASA's OSIRIS-REx mission, also stunned scientists with its comet-like behavior. Among the surprises was the asteroid's repeated emissions of dust and rock, similar to an active comet, as well as an unexpected rapid increase in the asteroid's rotation. As reported by New Scientist at the time, Bennu isn't a cold, dead rock after all. NASA's OSIRIS-REx spacecraft has spotted the asteroid spewing out dust and rocks on 11 separate occasions, over a period of just a few weeks, which was completely unexpected. For any newcomers, here is some quick background on the electric comet theory. As early as the early 20th century, the Norwegian experimentalist Christian Birkeland presented a theory of comets based on his experiments with gases in a discharge tube. He proposed that comets interact with what he called, quote, corpuscle rays from the sun, and the comets become negatively charged and produce explosive cathode jets, causing them to erode. A photograph of Birkeland's experiments can be seen on your screen. In the 1970s, the engineer Dr. Ralph Jurgens proposed that the sun was the anode focus of a glow discharge. This requires the sun to be a positively charged body relative to its galactic environment. In this view, a comet moving toward the sun from the outer reaches of the solar system develops a negative charge relative to its environment. While Thornhill later developed and modified Jurgens' model of the sun and of comets. The electric universe has proposed that differences in comet and asteroid behaviors are not due to differences in their composition, but rather primarily because of differences in their respective orbits. The displays of comets are not the result of sublimation of water ice and other volatiles on the comet nucleus, which have never been seen in the abundance that theory requires. In the electric universe theory, occasional comet-like activity has always been predicted to occur on asteroids. Although the orbit of a typical asteroid is much shorter than a comet's, and thus its activity should be more subdued, as with comets, such activity should result when an asteroid encounters any conditions that might cause a dramatic, quote, voltage spike, as was likely the case when the moonlit asteroid Dimorphos was struck by the DART spacecraft. Fundamentally, in an electric universe, it is not appropriate to view any body in our solar system, comets, asteroids, meteoroids, moons, planets, or our sun, as, quote, electrically neutral. A truly adequate background on the overwhelming evidence for the electric comet theory is beyond the scope of this video, so I encourage any newcomers to watch the feature-length documentary, The Electric Comet, available on the Thunderbolts YouTube channel, or the more recent 9th installment of my series, The Top 10 Reasons the Universe is Electric. Viewers can also explore the Thunderbolts playlist on electric comets and asteroids, which includes several dozens of in-depth presentations. I have to emphasize here that in the nearly 1 decade I spent as the writer, producer, and narrator of well over 400 episodes of space news from the electric universe, one of the most common themes I covered was the completely unexpected, from the perspective of standard astronomy, linkage between comets and asteroids, in both their respective appearances and behaviors. So-called active asteroids have put astronomers in the awkward position of attempting to explain cometary asteroidal behavior by mechanisms that are not cometary, since the view of comets as, quote, dirty snowballs has endured, despite all evidence to the contrary. Such was the case a few years ago, when scientists observed the asteroid Gault 6478 suddenly sprout not 1, but 2 dust trails. It also marked the first time astronomers had seen such a body shifting colors from red to blue. MIT scientist Michael Marcet said of the discovery, "That was a very big surprise. We think we have witnessed the asteroid losing its reddish dust to space, and we are seeing the asteroid's underlying fresh blue layers." A Phys.org report on the discovery stated, Marcet and his colleagues have also confirmed that the asteroid is rocky, proof that the asteroid's tail, though seemingly comet-like, is caused by an entirely different mechanism, as comets are not rocky, but more like loose snowballs of ice and dust. Michael Marcet stated, "It's the first time to my knowledge that we see a rocky body emitting dust, a little bit like a comet. It means that probably some mechanism responsible for dust emission is different from comets, and different from most other active main belt asteroids." These statements are genuinely confusing, since it seems that the scientists are not accurately remembering scientific discovery. First and most obviously, comet nuclei are not, quote, loose snowballs of ice and dust, as every comet nucleus imaged to date has affirmed. For another, Gault 6478 was certainly not the first time an asteroid astonished astronomers with its cometary behavior. As far back as 2013, I discussed with Wal Thornhill the, quote, baffling comet-like outbursts of the asteroid P2013 P5, seen by the Hubble Space Telescope, which astonished scientists with its unprecedented display of 6 cometary tails. Adding further surprise, the astronomers watched as the object's tail structures dynamically changed over just 13 days. Lead investigator David Jewett stated, "We were literally dumbfounded when we saw it." Even more amazing, its tail structures change dramatically in just 13 days as it belches out dust. That also caught us by surprise. It's hard to believe we're looking at an asteroid. In contrast, consider the asteroidal parallels seen on the nucleus of Comet Wild 2 in 2004, which was desiccated, complex and rough, rather than icy and smooth. A major shock was the presence of so-called impact craters on the comet nucleus. As reported by New Scientist in 2004, that is completely unexpected, because comets are believed to be loose aggregations of dust and ice that would shatter on impact. If the pits are craters, the surface of the comet nucleus must be much stronger than experts thought. NASA's Ray Newburn said of the discovery, "I don't think any of us ever really considered the possibility of impact craters. It may be a well-cemented rubble pile, but it's definitely not a loose, powdery surface." And of course, scientists on Earth were further astonished when Wild 2 dust samples revealed mineral inclusions that only form at superhot temperatures of thousands of degrees. As NASA curator Michael Zelensky stated, "That's a big surprise. People thought comets would just be cold stuff that formed out where things are very cold. It was kind of a shock to not just find one, but several of these, which implies they are pretty common in the comet." And yet, even though Wild 2 appeared more analogous to an asteroid than a comet, it not only behaved like a comet, its cometary jets were far more powerful and numerous than astronomers had predicted. A NASA report on the Wild 2 jets stated, The team predicted the jets would shoot up for a short distance, and then be dispersed into a halo around Wild 2. Instead, some super speedy jets remained intact, like blasts of water from a powerful garden hose. Mission scientist Dr. Benton Clark stated, "A big surprise was the abundance and behavior of jets of particles shooting up from the comet's surface. We expected a couple of jets, but saw more than 24 in the brief flyby." Again, the familiar behaviors of comets, including those displayed on asteroids, do not require the sublimation of the hypothesized, yet never seen in abundance, ices on comet nuclei. Comets have become active at impossibly vast distances from the Sun, including the observation several years ago of an active comet at roughly 1.5 billion miles from the Sun. At this point, we need to point viewers to the groundbreaking research of Dr. Franklin Anariba, a specialist in electrochemistry who has been presenting for roughly a decade his thesis on comet water production by electrochemical processes. As Anariba has shown, the complex plasma environments of comets, which interact dramatically with the solar wind, are the perfect conditions for, quote, water factories in space. Indeed, similar processes have been a part of the standard astronomical literature for some time, including attempts to explain the surprising abundance of water in the lunar soil. Along these lines, consider the research cited in the 2019 NASA report entitled "NASA Scientists Show How Ingredients for Water Could Be Made on Surface of Moon, a Chemical Factory." When a stream of charged particles known as the solar wind careens onto the moon's surface at 450 kilometers per second, or nearly 1 million miles per hour, they enrich the moon's surface in ingredients that could make water, NASA scientists have found. Plasma physicist William F. Farrell states, "We think of water as a special, magical compound. But here's what's amazing. Every rock has the potential to make water, especially after being irradiated by the solar wind." The report concludes, "A key ramification of the result," Farrell said, "is that every exposed body of silica in space, from the moon down to a small dust grain, has the potential to create hydroxyl and thus become a chemical factory for water. This explanation can ultimately resolve anomalies that will never be reconciled with the subliming dirty snowball hypothesis. This includes the detection of prodigious amounts of water from an obviously desiccated, rocky comet nucleus. The water is being created and is not the product of sublimation." As I mentioned earlier, in the 18 years that have passed since the Deep Impact mission confirmed numerous predictions of the electric comet theory, evidence in the theory's favor has grown substantially. A powerful example came last year with the publication of the doctoral thesis of scientist Sophia Bergman, in which she outlined new methods for observing low-energy ions around the comet 67P. The Rosetta spacecraft was equipped with an ion mass spectrometer, and Sophia Bergman describes her analysis of the data as follows. "For the first time, we have now been able to determine the flow directions of low-energy ions observed by ICA, the Ion Composition Analyzer, at comet 67P Churyumov-Gerasimenko. The results were surprising. We see a large amount of ions flowing inward towards the comet nucleus, instead of outward, as we had expected. As noted in the summary of the thesis, the Ion Composition Analyzer of the Rosetta Plasma Consortium measured positive ions in the cometary environment with energies down to just a few electron volts. The flow of positive ions toward the comet nucleus is strong evidence that the nucleus is negatively charged. As already stated, this electrical relationship between a comet and the solar environment is the predictive foundation of the electric comet theory. And so, as the scientific exploration of comets and asteroids moves forward with ever finer technological data, it is reasonable to hope that increasingly innovative scientific techniques will lead the way to a more advanced and true understanding of these celestial bodies, one which we expect will continue to affirm we live in an electric universe.